we're going to do a little introduction to waves in general, and then specifically for this unit, we're going to be relating it to sound. But you have different types of waves, which we'll cover in the notes. But generically, we draw them as a sine or cosine wave, and then they're going to look like this. And then there's a relationship between, change the color here, what we got V is wave speed. Sorry, trying to draw an arrow. Wave speed. We got lambda, which is the wavelength. Again, this is all covered in the notes in more detail. Length. So we got wave speed, meters per second. We got wavelength, meters. And then that, just to show you, you can do crest to crest. It's any cycle. It's anywhere the wave repeats. And then the variable is a lambda, Greek letter lambda. There's one there. There's another one here, right? Trough to trough. You could go equilibrium to equilibrium. That one's sometimes harder to find depending if they draw an equilibrium line, but that's wavelength. And then frequency, the last thing we got is how many wave cycles per second. So it's waves per second. So it's an inverse second, which we call a hertz. So it has its own, its units are seconds, but it's 1/seconds. And we named that after hertz. All right, so the relationship between all three of these is V equals F lambda. So, and some things stay constant. It depends on the medium. It depends on what the wave's doing in the medium. So we got, let's see, we'll do same. So same medium, and changing medium. All right, so if it's, switch up the colors here so it stands out a little more. If it's the same medium, that means the speed's never going to change. So in that case, V is constant. So I'm boxing it in to say that's never going to change. Speed of sound, for in here, we'll use 343 meters per second. So, so V sound. It varies, but for us, we're going to use 343 meters per second. It varies with temperature, pressure changes, density, that kind of thing. In there, this is speed of sound, air, I should specify. It will also change with different mediums. So if it's in the same medium, the speed's going to stay the same. And then what happens is frequency and wavelength are going to be inverses of each other. So as the number of waves increases, the wavelength between the waves is going to decrease. That's if it's in the same medium. If it's in a changing medium, we still have the same equation, V equals F lambda, but we're going to get something else is going to stay constant. So when a wave hits another medium, it's going to slow down. So the velocity is going to decrease. It's also, if you can picture these waves up here, these crests and troughs, when they hit another medium and they slow down, they're going to bunch up. So the wavelength is also going to decrease. And then what stays the same this time is the frequency. So F is constant, because the frequency is based on the source. And the source is somewhere out, wherever, sending sound waves. It doesn't know that there's a medium up ahead, or a medium change up ahead. So frequency just keeps sending waves, cycle after cycle. So the frequency stays the same for those. This one, speed is constant, V is constant. All right, so V equals F lambda is the equation. Now for this first challenge though, the probe is not going to give you the wavelength. It's going to give you the actual, you're going to get the time. We're going to do an echo. So instead of looking at the wavelength, you're just going to look at the distance. Oh boy. Sorry guys, that is trying to write distance. All right. You're just going to look at the distance. So all we need is one, the distance it traveled, and then the time, right? So v is going to equal distance divided by time, which is where v equals f lambda comes from. Let me jump around for a second. Where does v equals f lambda come from? Here, it's a little quick. So the equation's v equals d distance over time. So speed is constant, so it's just no acceleration, it's just distance over time. So v in this case is the speed of sound. We're going to leave that alone. Our distance in this case is the wavelength, so we call that lambda. And then time is a very specific time, it's the period. So we have the equation v equals lambda over t. Now the period, this is from the notes, is related to the frequency of 1 over f. So instead of saying v equals lambda over t, which is fine, that's another way to write this equation for this chapter. You can say v equals lambda over 1 over f, which is 1 over the frequency, and then when you divide by 1 over f, it just pops it up to the other side. So you get v equals f lambda. And then that's just the equation I prefer, but v equals lambda over t is also acceptable. For this first challenge, though, we don't have the cycles. All we have is the distance between, we're going to analyze an echo to determine the speed of sound. So the simulation will just give you the numbers, but if you were to graph it, you would get a big spike here. It would travel some distance, reflect off some surface, and come back to the detector. So the detector's back here somewhere, right? It would set off the detector, the original sound. It would go out some distance, and then reflect off a hard surface and come back. And when it comes back, it would spike the detector again. And then there's your t. So it's just v equals d over t from before, but we'll do more specific ones with v equals f lambda. But this first one is just how do you calculate the speed of sound. Little introduction. All right, guys.